Thank you, everybody, to come to the very last session of KubeCon in this room. We're really happy that you have the patience to stay here until the last moment. My name is Marc Tudurí. I'm a software engineer in Grafana Labs. And we're going to talk today about using eBPF for non-invasive instant network monitoring. Here's Mario.
Hello, I'm Mario Macías, also from Grafana Lab. I work in the same team as Marc. We work mainly on eBPF, and we are going to present how we use eBPF to provide monitor your network and your application at different layers of the network stack. I know many of you already know eBPF, but I'd like to do a small introduction how we are using eBPF in the Grafana Bela team. Basically, your application runs on top of or using a set of libraries, and it runs on top of the Linux kernel. Using it interacts to it with syscall, and the Linux kernel has a runtime that allocates the resources and operates your application. An eBPF-based solution like Grafana Bela to provide observability or security or networking, not concretely Grafana Bela, but any eBPF-based solution also runs as a user-level application, in the user space application, but it interacts with the eBPF implementation that runs in the kernel that provides verification and just-in-time compilation for safe access to the resources. It provides some maps to communicate the user and the kernel space, and some kernel helper API to interact and to load the programs. We are using many types of eBPF programs. eBPF is not something like, okay, I deploy a single program and it does everything. eBPF runs or injects multiple small and limited programs into different parts of your stack. In the operating system runtime, you can load network programs that in your network stack. You can run kprobes that will be triggered upon concrete or given kernel events, but also you can load uprobes. You can add probes into the application or the user space level application. This is in libraries or in the actual application executable. Good part of eBPF is that if you want to run eBPF or, for example, instrument an application, you don't need to rebuild the code of your application to inject the probes. You don't need to redeploy your services with the eBPF agent. It will be the eBPF solution who injects directly and transparently to the instrumented application. It has good native performance because it has a just-in-time compiled, and it also adds safety. eBPF pre-verifies your program to guarantee that the program will end and won't do some operations that could hang your kernel. But eBPF is not magic. It's not an SQL, or it's not a file system interface in where you can have information in a well-defined, stable format. It requires API-level knowledge of the instrumented targets. And when I say API level, I mean binary-level knowledge of the data. You don't have to think in a code level, but how the information is structured in a binary level. And also, eBPF programs are limited in size and functionalities. So instrumenting an application at the network level requires multiple small programs to be coordinated in a common effort. Grafana Bela is the solution we provide, is our approach for zero-code automatic instrumentation and network monitoring. By zero code, I mean without having to change or redeploy your application. It provides metrics at different levels of your network stack, like metrics about network connections, and also application-level metrics, following the OpenTelemetry specification about different services your application may carry, like HTTP, gRPC, Kafka, etc. We also provide traces at following the OpenTelemetry specification, also application-level traces. The network, as I said, is not instrumented as a single program that does everything. You need to install multiple programs in multiple small programs in different parts of your system. Those programs goes from programs in the traffic control or the express data path to get information from IPs, ports, packets, Ethernet addresses, interfaces. They will give you information about L3 and L4 layers. But this is very limited to connections. With kprobes in the kernel, you can get more information about IPs, connection, host names, and so on. And then if you go to the application level with uprobes, you can get richer information, like which protocols are they using, and even for each method call, arguments, payloads, return codes, SQL, etc. Anything that is visible through the internally. But instrumentation, even this is not uniform. I said it's not just installing a program and do it, but it's not also installing 4 programs and you have everything. Because, as we said, it is platform dependent. You need to know the binary organization, you need to know the runtime organization, and you might have different applications in your system using different technologies. So, for example, for C, Rust, and Python, I mention it because even if it's interpreted, it interacts with the operating system in binary level with syscalls. You might need a set of probes, but if you want to instrument Go and Java, you might need to hook your probes in other points or in other parts of your executable. Because, for example, some Go and Java bundle some libraries that other languages rely on the operating system, while Go and Java, for example, for TLS, secure connections, bundle their own libraries. Basically, with all this set of programs, what we have is a bunch of puzzle pieces, but we need to join them to give some sense to them. For network metrics, what you get is every time, for every packet, a program is run and extracts some information from your connections, source IPs, ports, destination IPs, destination ports, also other information like payload size, system interface, and so on. If you want, for example, to know how many bandwidth you have between 2 endpoints in your system, it's relatively easy because you have source IP, source port, destination IP, destination port. So you can group group all your packets, network packets, and aggregate this data. But one example of metric we have is Bela provides Bela network flow bytes that for 2 endpoints, it provides how many bytes are going in a given direction. But for higher level applications, it's a bit, or higher layers, application level layers, it's a bit more difficult because what you see is a bunch of, or a series of events coming from different programs. That means coming from a socket, coming from the TLS library, coming from the HTTPS library, coming from a Golang executable, and you get a bunch of events, but what you don't really care about, the events themselves are not so useful, are like individual puzzle pieces. What you want is to know the whole cycle of for example, an HTTP request, when it starts, when it ends, what method has called, what it returned, and those are pieces that come individually. You need to merge them, to join them. In classic web servers, there is an easy way. It's relatively easy. When I say easy, it's like, okay, it's not rocket science. You have a thread ID and a parent thread, so you can relate. You can get this information from eBPF. So even if you get events from different sources, you store them in an eBPF map, and then from the user space, you can read this eBPF map and join them by the thread. For example, classic old-style web servers accept a connection, create a new thread for that connection, and then carries the request from that thread. So using the thread ID, even if you have multiple events in the queue, using the thread ID, you can group which events belong to a single HTTP request. So here we might know that this HTTP request is a client-side request because we see this HTTP payload in the socket submission. So not in the socket receiving, but in the socket submission. So we know it's a client-side request. We know it's HTTP, just inspecting the payload that is extracted from eBPF. You can even know the method, the HTTP method, get users. You might know the payload size. You might know the response code, because for that same HTTP, for that same thread ID, you have another event later at time 143, it's just a random time, with the HTTP status. And you can know the payload time, and you can even know the total transaction time since the connection is created until the connection is closed. But luckily, but unluckily for us, modern web servers don't work that way. They use an even loop. They have a lot of, they have a small pool of threads, and they carry requests from that small pool of threads. So we need to also, the thread ID is not valid anymore, because the same thread might carry multiple concurrent requests. So we need to hook also in some implementation-depending functions. So we need to add extra eBPF probes. For example, for a Go standard HTTP application, we need to maintain a tree of parent-child Go routines, so we know we can relate the different events and can join the pieces according to the parent-child Go routines. In Node.js, you have this async ID, which is a similar ID. In Kafka, you need to maintain a tree of pointers to the different message handlers. So things start becoming more implementation dependent. We need to support or to explicitly add support to new or to other to new frameworks. Also, this has a problem, that is, if you have a library, if the library or framework internally is updated, because they optimize it, they find a more performant way to do it, your instrumentation might be broken. So you need to send us a GitHub issue, and we will fix it as soon as we can. So summarizing what we provide, network level metrics, L3, L4 are robust because they are based on stable APIs. Basically, the Linux kernel TCP IP library, and the binary implementation is a standard. So it's robust, but it provides very basic information, basically source and destination, how many bytes are flowing between two endpoints in your cluster. Application level metrics provides richer information, like methods, or might give better insights what's going on inside your application, but they have the inconvenience that it needs to implement explicit support to any new implementation or library of a protocol. And it's relying on internal implementation details that can change with time, so it's broken. It's also important to provide trace context propagation. This is an example of a single trace. This means that, for example, if a service gets a request and under the context of that request invokes request to other services, we want to get traces. For example, here we see a Chrome client that is invoking a front-end proxy. This front-end proxy is invoking a front-end, and you can get a better view. This is implemented using a trace parent header. This trace parent header is provided by multiple instrumentation SDKs or from the libraries that basically specify have good knowledge at the platform level or at the code level, have good knowledge of which request is related with which other client sub-requests. The problem is doing that in eBPF, since eBPF, as I say, has limited application level information. One way to do it is using an eBPF program in the network stack that when it detects, for example, in that case, an HTTP request, it will punch a hole in the HTTP buffer, giving space for adding a trace parent header. This trace parent is known, is already captured in another probes from the request, and using thread information and so on can relate that. But this won't work in TLS because in TLS we cannot modify a ciphered secure payload. So we are providing a novel approach based on IP context propagation based on IP packets. So when we have an IP packet, we punch a hole in that packet and add an IPv4 options. It's a part of the packet. We expand the packet, and Bela passes the context in that packet. However, this is a trace parent ID. And this doesn't fit in this. This IPv4 options is very limited. A trace parent, this is what is passed in HTTP header, for example, has a trace ID and a span ID. The trace ID is the group, identifies the group of requests, and the span ID is the individual request. So what we do is we remove all the information that is not the trace ID and pass this trace ID as an IPv4 in the IPv4 options packet. And then this is in the egress when the request goes out. But then in the ingress, we reconstruct the trace ID, but instead of, since we cannot inherit the span ID, we relate it with a given request using the span ID as the TCP len and TCP ACK, which we expect to be unique. So that way we can overcome secure connections and pass context. The inconvenience of this is that this works with this allow Bela interacting with other SDKs, all the OpenTelemetry SDKs, while this requires that all the services are instrumented with Bela.
Thanks, Mario, for the detailed explanation. Now I'm going to proceed to talk about how we make all of this network monitoring sense in the context of Kubernetes, because that's why we are here for in KubeCon. So what Bela sees at eBPF level, as Mario mentioned, is that it's like very basic information. At network level, we work with addresses and ports, either for source and destination. So we have this with graph. And for application metrics, in this case, for example, we have HTTP server request duration. We are able to track how is the latency for this route. But in this case, as a service name, we capture Java, which is the command line for this application. But this is not enough for us. What a Kubernetes user needs in this case, for the case of network metrics, is which Kubernetes services are calling which. So, for example, we have a service front end in the namespace app that is calling a database service in the storage namespace. And for the case of application metrics, we want to know that service that it was running in Java was actually the inventory service running in the backend namespace. How do we handle all of this? Well, Mario mentioned this in the previous session, but I'm just going to recap. We use a Kubernetes abstraction called informers, which is provided in the Kubernetes API Go client. And basically, it allows us to subscribe to events happening in the Kubernetes cluster. In this case, we are subscribed to pods, services, and nodes. And the kubelet is going to respond us every time there is updates in when you create, update, or delete any of these entities. Then in Bela, we maintain a map of IP addresses and resources, and process ID and resources. And like, be careful with this, because it's that, like, if you have a cluster with a few nodes, it's fine, but if you have a cluster like us with 1,000 nodes, we can create an outage, so it's better to use the cache that Mario mentioned before. So, yeah. So how do we match all of this process information with Kubernetes information? So what eBPF sees at Bela instrumenting an application is very basic. It's just the PID and the command, as we've seen before. But in Kubernetes Vault, we have what we want to see, which is the name, the namespace, and all of this stuff. So thankfully, we are able to, thanks to the process file system, go to, with the PID to fetch specifically the C group. And with the C group, we are able to relate, thanks to the container ID, the process information with the pod. Okay, we can also do some interesting things like track inter-zone traffic. That means that we can, thanks to this network observability, inspect which zones are calling with others in the different clusters. And this is very interesting because we can calculate how much is the cost, like we can infer the cost between zones. Yeah, so this is basically, we just go to the pod and we are able to get the node name. And in the node, there is this label, topology Kubernetes zone, and fetching this data, we are able to enrich our Bela network flow bytes with the source and destination zone. And we can even create a new metric, which is the total of bytes between zones. We are also able to track external traffic. For now, we were just like tracking like traffic from services to service inside the same cluster or cross zones, but we are also able to track external traffic. For example, here we have a ping to golang.org. It's going to return an address, and we can do an NS lookup to get the host name for that IP. In the context of Bela, let's imagine that we have an instrumented application here, and this we are doing a pull request or HTTP request, whatever, to golang.org, and this goes to the DNS server. This is going to return some information like the host name, and thanks to Bela and eBPF, we're going to tap into this call, and we're going to enrich our network flow bytes with destination name. Instead of an IP, we're going to say the DNS, like the host name here.
Yeah, the good part here is that using eBPF to sniff onto the DNS traffic allows you to get the actual name. If we were using a namespace lookup, we will decorate, instead of golang.org, we will decorate it with this gibberish, math, whatever, that is what is actually returned. So thanks to eBPF, we can provide a more accurate local reverse DNS.
this is very cool. We are getting a lot of information thanks to the network monitoring, but if you enable Bela in your cluster, it's going to start to explode the cardinality because there is a lot of labels and a lot of metrics that we're starting to enable. But thankfully, we provide in our config like a way to, for a specific metric, indicate which labels we want to include or we want to exclude from the collection of metrics. And you maybe are wondering why, what's the utility of all of this? So thanks to Bela and the network monitoring, we're providing the data to one of other Grafana products, which is Grafana Search. And one of the features that Search has is this Entity Explorer, which allows you to see in all the entities of your cluster how are connected to each other. In this case, we deployed in our cluster this project from OpenTelemetry called OpenTelemetry Demo, which showcase an e-commerce where there are many microservices calling each other. So we deployed OpenTelemetry Demo in a cluster. We enable Bela, and we have this. So you can see how the different services are calling each other, and then you can have a better understanding how is the topology of the network in your cluster. This is very important, but thanks to the shoulder of giants, that's how we built Bela. Initially, Bela was a fork of OpenTelemetry Go instrumentation that was covering the application layer. And with time, we evolved to we added more features, and we went beyond Go. And now we are able to do application monitoring for any kind of programming language. And for the network part, we did a successful proof of concept after a hackathon, taking inspiration from this project called NetObserve.io. And basically, Bela is doing the combination of these two amazing projects. And Grafana has a core values, open source, and community. So we were very keen to donate Bela back to OpenTelemetry, and we initiated a donation in October last year, and it's been ongoing for a couple of months. And thankfully, we are reaching to that the donation is very well accepted, and in the upcoming months, we plan to finally set up the whole community around what would be eBPF auto-instrumentation, OpenTelemetry project. And that's it, and thanks a lot for your attention, and if you have questions, please.
Questions, then? No. Okay, thank you very much.
Thank you.